Hi, today we'll be talking about the process control in palm oil industry.
Palm oil is extracted from the fruitlet of a specific oil palm species known as Elaeasis guineensis. The harvested fresh fruit bunch from the palm trees has a stalk and a palm fruit. Each palm fruit consists of the pulp, shell, and kernels, where the oil will be extracted. Palm oil is semi-solid at room temperature. This characteristic is due to the 50% saturation level of the oil. Palm oil has good resistance to oxidation, hence able to be heated at prolonged elevated temperatures. Besides cooking oil, palm oil is also used in personal care and cosmetics, biofuel and energy, and pharmaceuticals industry. The palm oil is indigenous to West Africa. It was brought into Malaysia and now it is one of the major producers of palm oil, where Malaysia currently accounts for 39% of the world palm oil production and 44% of world exports.
The fresh fruit bunches (FFB) is transferred into the sterilizer using a conveyor belt and steam is added to cook the bunches in a cylindrical pressure vessel for about 60 to 90 minutes. The heat will stop the increase of free fatty acid and weaken the fruit stem for mechanical stripping. The sterilized FFB is sent for stripping process. Commonly used stripper is a drum stripper, which has a long horizontal cylindrical drum that is rotated fast enough to lift the stalks using centrifugal force. The inner lining of the drum is fitted with T-bars that are spaced just enough for the fruit to pass through, leaving behind the stalk. This process separates the sterilized fruit from the bunch stalks. The next process is digestion, which reheats the sterilized fruits to loosen the pericarp from the nuts in preparation for pressing. The digestion is carried out in a steam-heated vessel that has rotating shafts which have stirring arms to agitate the fruit. Then the screw press, which is basically a perforated cage that has either a single or double screw. The screw will restrict discharge from the cage, which creates a pressure within the cage. This controls the amount of de-oiling of the smashed digestion. The screw press lets out a liquor of oil, which contains impurities and also a press cake. The oil will enter a vibrating screen to remove the coarse solids, and the remaining oil will enter the clarification tank, which is a gravity settling tank. In the clarification tank, the oil and sludge are separated. The sludge from the clarifier has about 10% of oil remaining, which is mostly recovered by using a centrifugal separator and returned to the clarification tank for further treatment. The oil from the static clarifier will enter a purification process beginning with a centrifugal purifier which reduces the dirt content to 0.01% or less. Then the purified oil is dried in a vacuum dryer to bring the moisture content down to 0.1%. The crude palm oil is stored in a storage tank. The press cake from the screw press is then fed into a vertical column called a depericarper, which uses a cyclone of air to separate fiber from nut. The nut will enter the next stage, which is called nut conditioning. This is achieved by first drying the nuts to loosen the kernels and then cooling them to harden the shell. Then a centrifugal cracker is used to crack the nuts and remove the kernel. The cracked mixture is separated into two operations. First, a dry operation that uses a winnowing system to remove small pieces of shell and dirt, then followed by a wet separation using a hydrocyclone to separate the kernel from the shell using centrifugal force. The last step is to dry the kernels to about 7% of moisture content to reduce the chances of mold. The dried kernel is bagged and stored.
We'll be focusing on three major equipments, which are sterilization, clarification, and vacuum dryer.
In the extraction of palm oil, sterilization is the first process. Sterilization is a cooking process of FFB using pressurized steam. The sterilization process is employed for several reasons. Number 1, to detach individual fruits from their bunch. Number 2, to deactivate enzymatic reaction that forms free fatty acids or FFA in the oil. Number 3, to disintegrate oil cells in the mesocap and condition the kernels. Any problem here propagates into the subsequent processes. For instance, insufficiently cooked FFB might have fruits intact to their bunch, hence they cannot be stripped. Besides, overly sterilized FFB over-tenderizes the fruits and cause oil losses. Sterilization unit includes a long cylindrical chamber, loading door, and rails covering the length of chamber. FFB are filled in carts so it can be easily pushed in and out of chamber. Prior to elevating chamber pressure, steam of lesser density is transmitted to remove air. During sterilization, some of the steam is condensed, hence fresh steam is introduced for heating. Fresh steam is kept at 30 to 40 sec and process duration is 60 to 90 minutes. The main objective of sterilization is to reduce oil loss. This can be achieved through image processing control and pressure control. FFB supply received by meals comprise of ripe, overripe, underripe, rotten, and empty fruits. Different ripeness of fruit should have different residence time to achieve minimum oil loss. According to an optimization study, Case 1 and Case 2 indicate increase in FFA ripeness would reduce oil loss and FFA content, though higher overripe FFP content causes increased oil loss and FFA content. In Case 3, where the percentage of overripe FFP is high, the decrease in sterilization time and pressure peak can reduce oil loss. Therefore, it can be deduced that Higher percentage of overripe FFB should have lower residence time in sterilizer as compared to ripe FFB. Industries use time-consuming manual grading of FFB. Digital image processing can be used to estimate FFB ripeness by estimating its oil content. After determining FFB ripeness, number of peaks necessary can be determined too. This can be done by taking images of FFB and converting them into digital number values representing three color bands, red, green, and blue, by using software analysis. The control strategy is a feed-forward control to control oil loss by measuring the disturbance variable, which is ripeness of FFB, and manipulating the speed of conveyor belt. If DI sensor produces red color band, the FFB is overripe. Signal is sent to controller to increase the conveyor belt speed so that the residence time is shorter. If blue color band is obtained, controller will reduce conveyor belt speed for longer sterilization. If green color band is obtained, normal processing time is maintained by conveyor belt motion. Sterilization consumes large amounts of steam that are expensive, hence optimizing peaks of sterilization reduces cost. Sterilization has specific pressure peak configurations. The pressure inside the chamber will increase to 40 sig and reduce to 0 sig for 2 to 3 cycles in order to reduce oil loss. The control strategy is a feedback control that controls the pressure in the sterilizer by manipulating the flow rate of the steam inlet. The temperature of the steam is the disturbance variable. During sterilization, the steam is trapped in the chamber. The pressure in the sterilizer is measured using pressure sensor. If initially the pressure is lesser than 40 sig, the control valve of the inlet steam will increase the flow rate in order to increase the pressure in the sterilizer. Once 40 sig is reached, heating is stopped for the steam to reach 0 to 5 sig before being replaced by fresh steam. This control system provides only sufficient heating, as overheating causes oil loss. This control system also prevents oil loss that may contaminate the environment.
Clarification is one of the main processes in palm oil mill. This process separates crude oil from its impurities in a settling tank through gravity. The vertical clarifier has a conical bottom. The viscous crude oil is diluted with hot water before entering the clarifier. The diluted crude oil, known as DCO, will enter the vertical clarifier at the middle, in between the oil layer and the sludge layer. The oil layer will build up and the adjustable oil skimmer will skim off the oil. The sludge will collect at the bottom of the tank and discharge. A stirrer is attached at the bottom of the clarifier to separate oil from sludge. A steam heating coil is fitted in the clarifier in order to reduce oil loss. The main objective of the clarifier is to achieve maximum separation efficiency of the oil and the sludge. There are three main parameters that will affect the separation efficiency. First, temperature of the mixture. Second, dilution of the oil. And third, the concentration particles in the tank. Temperature control in the tank is achieved through a feedback control loop where the control variable, which is temperature of the mixture, will be controlled by manipulating the inlet flow rate of the steam. The disturbance variables in this system are the temperature of the steam, temperature of DCO inlet, and heat loss to the surrounding. For the process control, the temperature transmitter will be attached to the inside of the tank. The transmitter will transmit the measured temperature to the temperature controller in order to compare it with the set point, which is in between 90 to 95 degrees Celsius. The error signal will be transmitted to a control valve to adjust the inlet flow rate of the steam. When the temperature is higher than the set point, the flow rate of the steam at the inlet will decrease. This control system is able to ensure that the temperature of the mixture remains at 90 degrees Celsius. This is the optimum temperature to enlarge the density difference of the oil and sludge to achieve separation within the detention time. Hence, this will allow a higher production capacity. The second process control is dilution control for DOC. The dilution control is done by a feed-forward control system. The composition of DOC mixture will be controlled by altering the flow rate of inlet hot water. The disturbance variable in this system are the inlet flow rate of water and the composition of water in the inlet crude oil. The flow rate sensor measures the hot water flow rate and transmits the signal to the flow controller. Another flow rate sensor will measure the inlet flow rate of crude oil and transmit the signal to ratio station. The optimum dilution of water to oil ratio is 3:1. The signal sent by the ratio station to the flow controller will act as a set point in order to manipulate the flow rate of hot water. Dilution provides a barrier causing the heavy solid to settle to the bottom and the lighter oil droplets to rise to the top. However, excessive use of water will result in poor settling rate and high oil losses. This system increases the revenue by reducing the oil loss. The last control is a sludge level control. The sludge level in the tank is controlled using a feedback loop by manipulating the outlet flow rate of the sludge. The disturbance variable is the inlet flow rate of DCO and the composition of sludge in the DCO. For the process control, the level sensor for sludge will measure the level of sludge in the tank and transmit the signal to the controller. The level control will compare the measured value with the set point. The controller will transmit the signal to the control valve of the sludge to manipulate the outlet flow rate of sludge. High concentration of particles in the tank will prevent the particles from settling. Hence, this control system is able to reduce the residence time needed and therefore increasing the production capacity.
Vacuum is often employed as a process for removing bulk and absorb water from a product. Combined with heat, vacuum can be an effective method for drying. High degrees of dryness can be attained at relatively low temperatures. This allows for fast and effective drying of temperature-sensitive products. The oil to be processed from purifier will be injected into float tank. In this float tank, there is a taper spindle that serves as automatically valve to keep the constant vacuum in the vacuum chamber continuously. In vacuum chamber, there are 6 spray nozzles that inject oil to deflector surface. The oil released from spray nozzle is in spray shape and cloudy, and then falls through gravity and strike the deflector plate to allow the second cloudy. During oil in cloudy shape, the concentration of moisture will be easily vaporized and sucked out by vacuum pump. The dry oil will be then fallen into vacuum chamber bottom and removed directly by pump to storage tank. The objective of level control of oil is to prevent overflow and contamination of oil at storage tank. The control variable, which is level of oil in the chamber, can be controlled by manipulating the outlet flow rate of oil. The disturbance variable is the inlet flow rate of oil. A float valve is connected into vacuum chamber serving to control the level altitude of oil. When the oil level is low, the level control will automatically open the valve to allow oil to be recirculated into vacuum chamber through bypass piping. When the oil level is high, the oil will be directed to the storage tank. Level control of oil is important to prevent overflow, as this will damage equipment and lead to loss of oil. Level control can also prevent unprocessed oil to be removed from the dryer. This can prevent contamination of oil in the storage tank. The objective of temperature control is to maximize the drying efficiency. The control strategy is a feedback control. The temperature of vacuum chamber is controlled by manipulating the inlet steam flow rate. The disturbance variable is the inlet flow rate of crude palm oil and steam. During drying process, the temperature of chamber is measured using a temperature sensor. If the temperature is lesser than 75 degrees Celsius, control valve of steam inlet increases the steam flow rate to raise the chamber temperature. Conversely, if the temperature exceeds 80 degrees Celsius, control valve of steam inlet reduces steam flow to reduce the chamber temperature. The purpose is to ensure the temperature of crude palm oil remains at certain temperature by applying heat to maximize drying while preventing freezing of liquid, and also to ensure the efficient use of energy for the process and lead to cost reduction of process. The last control system is pressure control. The control strategy is a feedback control to retain the vacuum pressure conditions in the drying chamber. The control variable. Vacuum pressure in the chamber is manipulated by altering flow rate of incoming oil. The disturbance variable is the outlet flow rate of water by the vacuum pump and the moisture content of oil. For bounded moisture, longer time is required for the moisture to vaporize. Hence, this will increase the residence time of water in the tank and increase the pressure of the tank. The pressure transmitter is used to measure the pressure in the tank. The measured pressure is compared with the set point at the pressure controller. If the pressure is higher than set point, the controller will send signal to the control valve of the incoming oil to reduce the flow rate. This control can increase the effective delta T by reducing the boiling point since the pressure is low. Thus, drying of the material will be faster. This can increase the production capacity.
This is the end of the video. Thank you.